So, we will be continuing our discussions again on recrystallization, and we will today do some discussions on growth or rather grain growths. As you know, recrystallization kinetics is very important, and that is why I introduced a new topics in the last class, that is the Johnson-Mehl-Avrami type of equations which can describe the growth, nucleation growth both for different kinds of situations. And the fundamental equation which I have discussed in the last class is very simple. It tells you the fraction transform y. Okay, it can be any transformations, whether it is new grains from the deformed grains or even a new product from a parent phase. So, it is equal to 1 minus exponential minus k t to the power n. So, in which y is the fraction transformed, k is a constant and t is the time and n is another exponent. So, k is normally given by very simple, in a growth situation we have seen this is equal to pi by 3 n dot is the nucleation rate, g dot is the growth rate to the power q. This is the constant k. It can vary from different situations. We will discuss two such situations and give you a detailed list how k and n can be changed. Now, n is known as the exponent, as you know here in this equation, exponent, and for most of the situation n is equal to 4, but it can be less than that value also. So, important aspects in understanding the kinetics of such a kind of equation or transformation is basically to determine the values of n and k. As you know, n is the time exponent. So, therefore, n has a stronger effect on these whole transformations. As the n increases, transformation become faster. So, there are two important situations which we should deal with it. I will give you example. One I have already given, another two example I will give today, I have listed down from this book. Okay, let us consider a situation, very simple situation. Okay. Let us consider a situation in which you have a pre-existing nuclei in the material. Okay. It can be pre-existing nuclei of the recrystallized grains already present, it is possible. In the recovery stage, these grains might have been nucleated, okay, just nucleation. And then subsequent thing what happens is that as we increase the temperature, the growth takes place. So, predominant aspect is that growth happens from the basically at the beginning. So, growth happens from the time tau is equal to 0, time tau is equal to 0 and to the time tau is equal to t. Okay. So, that means from the beginning itself growth happens, and the such a situations is very simple to do that. And also we also assume that after the growth started there is no further nucleation. So, that means n dot is basically 0 after the time tau will to 0, obviously, because all the nucleating things, nucleation events which was there, nucleating nuclei, they are already present, they are not changing anymore. So, that means it is a completely growth control phenomenon. So, in such situations it is very simple that the volume transform of the new phase beta, which I have discussed in the last class also, is basically equal to m0, which is a constant. I will tell you what, multiplied by volume b, then g dot q t q, okay, and this has to be multiplied by 4 pi by 3, it is a constant term. Okay. So, why it is so? Here m0 is the constant nucleation rate, it is not changing. It was there at the beginning of transformation, all the nucleation was there, nucleation rate per volume, and that is why you multiply by b, and gq is there. Remember, t, the exponent of t has reduced from 4 to 3 here. That is because it is very simple. Once you have a pre-existing nuclei, it can grow only in 3 directions, x, y, z. So, there has to be 3 components of the different growths, and because of that it is only 3 as exponent in the time scale. So, that means what? In such a situation where you have pre-existing nuclei present already and the change of volume fraction of the phase or volume fraction of the new phase form is directly proportional to the t to the equal to or equal to t to the power q, when these things are actually normally constant. M0 is a constant, volume is constant, also G dot is normally constant when it is growing isotropically as a spherical manner into the phase. The one picture is there all on the slide, you can see that. So, this is one particular situation which is by there. Now, y is obviously equal to 1 minus exponential, you know that is basically equal to 1 minus exponential b b e by b, where this is the they are the 2 different volumes, one which is apparent volume, another one is the actual volume and that is equal to 1 minus exponential minus you know is equal to minus k t to the power q, and here k is equal to 4/3 pi by 3 m0 v and g dot q. Okay. So, this is one situation in which nucleation has no role to play, that is why n dot is not present even anywhere in the equation. It is only G dot which is determining the things. Now, obviously when you are talking about the growth, it can be dependent on the transfer of the molecules from the parent phase to the product phase, and that can be differing, that can be different for different types of transformations. If it is completely dependent on the gain boundary diffusion, then this one will change. If it is completely dependent on the volume diffusion, it will change. So, those are all subtle issues which can be dealt with separately, but fundamentally this is how things happen. So, this is how one can apply these things. This is I write case 2. Case 1 I have already told you. Case 1 is basically where this is pi by 3 n dot v g dot t to the power 4. That is what I have discussed in just now. And case 3 is basically a situation in which both nucleation and growth are involved. So, case 3 is suppose you have a very small fine grained crystals, okay, very small fine grained crystals. That means you have a large number of gain boundaries, okay, because of the fine grained crystals boundary area is large, and nucleation always happens at the gain boundaries. We know that, or gain edge corners, or the gain edges, or gain corners, or the triple points. This is the places of heterogeneous nucleations happens. So, nucleation will takes place randomly. If the gain boundary characteristics is random, that means gain boundaries are not Pesal type. Pesal type means it are not sigma 3 type gain boundaries, it are basically it are random gain boundaries. In those cases nucleation will also happen randomly along the gain boundaries. So, once the nucleation actually happens along the all gain boundaries and it is exhausted, suppose all the gain boundary areas are filled with these nuclei. So, there is no further nucleation possible along the gain boundaries. So, only possible chance is then having a nucleation inside the grain, and that is very less likely because of the energetics of the system, which we have discussed in many times in that earlier lectures. So, in these cases what will happen? When the gain boundary nucleation exhausted, then growth will happen only. Now, as you understand, when such a situation happens, when the growth actually is taking place on the from the nuclei along the gain boundaries, growth is basically will be happening along the direction perpendicular to the gain boundary. That is obvious, as you have seen, basically very simple. Suppose you have a gain boundary and you have a nuclei, okay, like this, and this nucleus has a coherency along the gain boundary and incoherency along these. So, this growth will happen perpendicular to the gain boundary, that is obvious. So, that is what you see in many cases, these things form Widman-Staton structures, we have seen in the case of steels also, and this is very common. So, therefore, if this gain boundary is completely filled by this nuclei and no further nucleation is possible, the growth will only happen in the direction perpendicular to the gain boundary, correct. That means growth is one dimensional. In such a case, n become 1 because it is only happening in one direction. So, growth will be much slower. So, only way it can actually grow is perpendicular to this. So, if I draw this picture again, so therefore, they will become like that, they will become bigger, these crystals but they are only growing along one directions. Okay, although I have drawn little bit bigger in this direction, but mostly they are growing along these directions. So many such transformations like cellular precipitations or growth of Widmanstatten plates happens by this mechanism. So for this situation n is equal to 1, and very simple. Why? Because it's one dimensional growth. So you have seen when you have 3 dimensional growth, okay, here on the px nuclei, 3 exponent of time become 3. So that means this exponent of time is basically telling you what are the different modes of the growth. If the modes of the growth are actually multiple, then this becomes more than 1. If it becomes singular, then it becomes 1. So that is the difference you should know very well in the literature. And so thus, depending on different situations, we can actually have a table, and I will do that. You should be very clear about it. Depending on the different situations, these exponents can be changed. So let us put a tabular format, because we have discussed many other transformations previously, and we can make a table and tell you. So I will tell you that different types of situations, nucleation and growth, very early stage, okay, and late stage. That means at the beginning and the later, okay. And so therefore what I will do is that these are the different situations, and values of n will be provided for these two, very early stage and very late stage. So when you have homogeneous nucleation, which is very rare, first one is a homogeneous nucleation, which is very rare. It happens only in some very small cases. Early stage it is going to be 4, late stage also it is going to be 4. So nucleation happens well inside the grain, so it can grow in all directions obviously. Along with nucleation is not actually stopped. See what happens is the nucleation and growth takes place simultaneously, many of the situations, many of these transformations. That is why n become 4, because you have 4 different things, different rather directions. One is nucleation, the other 3 are the 3 growth directions. That is why n become 4. Now if you have a pre-existing nuclei already and they grow, that we discuss. So initially it will be 3, and let us say also it will be 3, because it is nothing but 3 dimensional growth along happening in the 3 directions x, y, z. Randomly distributed heterogeneous nuclei, randomly distributed. This is a situation just I discussed, the second one, randomly distributed heterogeneous nuclei. For that, it can vary depending on 3 to 4, because either nucleation can happen together with the growth, or nucleation can happen and then growth takes place predominantly. But it can reach 3 at the later stage, because nucleation will no longer happen at later stage. So it is only growth in 3 directions. So situation 1, 2, 3. Now situation 4 is basically nucleation along gain boundaries. So I simply write gain boundary. So what will happen? If it is along gain boundaries, obviously initially both nucleation and growth can happen. So that is why it is 4, but later stage it will be 1. That I told you, when all the gain boundaries will be filled by the nuclei, no longer nucleation is possible, and growth can only happen along perpendicular to the gain boundaries. So that is why its n become 1. This is a very special case. And 5 is basically gain edge. What is gain edge? As you know that edge means the where there is meeting points of the grains, and 6 is basically gain corner. It is all we discuss in nucleation. You should go back and see the lectures. and this will be 4 and this will be 2. Obviously, then growth can happen along 2 perpendicular directions because it is an edge. So, you have 2 perpendicular direction, and here it can happen along 3 perpendicular directions because this is a corner, and these 3 grains have meet together. So, it can happen. Only thing can happen is that the nuclei will be having orientation relationship with one of the grains, other 2 may be not having any orientation relationship, they can grow freely along these directions. So, these are the values of the n's along different situations possible in the different phase transformations depending on the nuclei, and these are can be calculated using the this can be used to apply the Johnson-Mehl-Avrami equation, understand different phase transformation. This is very important, and this picture basically is a recrystallization, and you see here the nucleus or most of the nuclei has formed along the boundaries and the gain corners and the edges normally. So, that is this is very common, and then these nuclei have grown and then they have reached the critical size. Now, next thing which I will discuss whatever time I have next 10 minutes is basically the growth. As you know, this Johnson-Mehl-Avrami equation considers both nucleation and growth because it is talking about fraction transformations, but in recrystallization how the growth actually happens. Suppose initially you have large number of grain boundaries because of the small grains, and these boundaries are very large. So, because the area is very large, so therefore, the energy of the boundaries are also large. So, therefore, it is obvious that these boundaries will the area will reduce, and only way it can reduce is by going the grains, okay, or by making the grains bigger. And therefore, this process is very spontaneous. This process is very spontaneous. Why? Because it is already small grains has large area, so they will always try to reduce these things. It is simple like if you create bubbles in these soap bubbles in a bucket, you will see initially number of soap bubbles will be very small, and then slowly they will try to reduce its surface energy by simply coalescing together. Whether such a thing happens in the gain growth or not, okay. Really this thing happens, let us consider that a system in which all the boundaries have same energy. That means boundary energy can change depending on the characteristics of the boundary, but let us assume they are all same. If that is the case, then then what will happen? As you know that grain edges in the system will form by the 3 grains when they were their meet. Okay, let me just show you the picture here. So, grain edges can easily form where the 3 boundaries meet. These are the grain. Okay, you can see that actually. So, equilibrium angle when the 3 of them meet. Okay, 3 meets means what? Equilibrium angle of when the 3 of them meets is basically, you can see that is basically. Let me draw it properly. This angle is basically must be 120 degrees. That is the equilibrium angle, and using Lami's theorem one can show that that is because the energies of these boundaries must be at equilibrium, and that is only possible when the angle is 120 degrees. Now, question is this is only satisfied, this 120 exactly is only satisfied when the number of sides of the grain is 6. That means when it is a regular hexagon, that is all, then only the angle will be exactly 120 degrees, and if it is less than 6 sides, angle will not be 120 degrees, and in order to make the angle 120 degrees, these will form what is known as, they will curve, the boundaries will get curved, that is what you see, and these curved boundaries when it is less than 6 edges will be convex. Okay, you can clearly see they are like a convex boundaries. But when its number of sides are more than 6, and then still the 120 degree angle can be maintained again by making the boundaries curved, but the boundaries will become concave, right, you can see that. So, 6 is a critical number of sides a grain can have in which equilibrium angle of 120 degree can be maintained. When it is less than 6, then the equilibrium angle of 120 can be maintained by simply making the boundary, by making these skin boundaries curved, and curved in such a way that their radius of curvature will be such that it looks like a convex, but only when it becomes more than 6, the number of sides of the grain, and in this case it is 1, 2, 3, 4, 5, 6, 7. Still the angle can be maintained 120 degrees for equilibrium, but then the curved boundaries will be concave. So now what will happen when such a, because in a random situation you can have boundaries starting from 3, 4, 5, 6, 7, 8 or maybe even more. Even those who have looked at the grains properly, you will see in optical microscope, even if you look at iron grains under an optical microscope, it's all kinds of grains of different sides, number of sides are possible. So what will happen then? Let us look at that. Before I go into that, I just wanted to discuss with you something that, if let us take a situation, so this simple thermodynamics. Let us take a situation, that is a classical situation in which I have an alpha phase, big grain of alpha, very big grain of alpha suppose, okay, and this is alpha, and suppose inside that I have a small grain, okay, and suppose this is also alpha, this is alpha, and it has n prime number of moles, and rest of the alpha has n double prime number of moles, correct. Now we are going to look at a situation in which the mass is getting transported from these small alpha grain to the outside, and suppose if this much small mass dn number of molecules is transported, what will happen to the equilibrium situation? This is a very simple situation, not difficult. So initially the total free energy of the system is what? Total free energy of the system is obviously equal to number of moles n prime, or rather let me see, these equations are very simple but needs to be written properly, I should not make any mistake. Okay, so this is the free energy, G is the free energy, or write the G alpha, okay, plus this interfacial energy. Interfacial energy means what? Because of this interface between two alpha grains, there is interface, and I am writing it in general. I do not know how many interfaces are there, ai, gamma I, but I can vary from 1 to anything, because you can have large number of such grains present inside these big alpha grain, okay. That's how the grain growth happens, and so this is the total surface energy contributions plus n double prime multiplied by G alpha. N double prime is the mole of the rest of the alpha, the big grain, and G alpha is the G free energy of the G. This is the G of the system. Now very simple, suppose if such a situation happens when dn prime number of moles is getting transported from inside these grain to the outside. So what will happen to the change of the free energy? What will happen? It is very simple. Obviously G alpha is not going to change, it does not depend on that. So what I am going to change is this plus summation that is what it is. So this is the area dependent term, and this is the basically the because of the big grains outside for that change. Now as you know, mass needs to be conserved, so therefore dn must be equal to, this must be equal, whatever mass is getting transported there is the mass gain to the next grain. Whatever is getting transported from small grain dn prime is basically added to that. So there is no mass loss. So therefore whatever addition we are doing because of a change of the molecules of moles of these big grain n double prime, that is the change dn double prime, that must be equal to dn prime. Well, let us suppose this is dn. So I can write down dg system is equal to nothing but, very simple, nothing but minus gamma I dai by dn prime, or rather dn into dn. That is what I write down. Okay. Now, if we consider a sphere, already we have considered sphere, and know the volume of the sphere, area of the sphere. Okay. Volume is 4/3 pi r cube if r is the radius, and area is equal to 4 pi r square. You can convert, find a relationship between volume and area. It's very simple. You can do that. Let us not do that. So, for the sake of the time, I can write down this change. We can write down in terms of delta G. Remember, this is d. D is small and delta is big. Nothing but this is infinitesimally small. This is small. So, we can write. We can see that this will be equal to twice gamma b by r multiplied by dn. It's very simple if you consider one grain with this volume and this area. So, what does it say? It says that P&G change is always negative. That means mass will be kept on getting transferred from this small grain to the outside. Okay, and slowly this boundary will be wiped out. There will be no such boundary. And it also tells you that change of delta G is negative. Why? Because gamma is the interfacial energy, is positive, volume is also positive, r is also positive. None of these are negative. And because you have a negative sign at the front, therefore the whole change of the P&G is negative. So that means this process is spontaneous. You don't have to provide, you don't need to make it the process happen. It only depends on the diffusion, how fast you can do that, because mass transport depends on the diffusion. But thermodynamically, this tells you process is possible. Another important thing, it tells you smaller the r, higher the value of G. So that means smaller the radius of curvature, higher the value of G. So now let us use this analogy to explain that, explain the grain growth mechanism here. It's not very difficult to understand here, as now I have given you the whole concepts. So that means what? As you know, if I have grains with less than about sides less than 6, and these grains will slowly, it will have a convex curvature. So that means what? The grains will slowly shrink. Why? Because r will increase, keep on, if this boundary is moved to the center. Okay. Then that means all the grains which has a side less than 6 will slowly vanish. On the other hand, these grains, because the radius is center of curvature is along these boundaries will move like that. That is obvious. That is why in a grain growth situations, the grains which is boundary less than 6, they are consumed by the system, or they simply vanish from the system, and the grains which is the sides more than 6, they grow. This is the basic aspects of the grain growth, which you must, please, you must know this, because this is very fundamental concepts. And that is how actually grains actually grow in the actual materials, and that is how actually they grow. Now one can actually look at the detailed kinetics of the growth, which we will do in the next lecture, but that is not very difficult. That is also diffusional aspect, so it is not extremely difficult to do that. But the fundamental things which you should know, why a grain with size less, number of sides less than 6 will grow, and grains will not grow or will get shrunk, and the grains with more than 6 sides will grow. This is very important. This comes from the thermodynamics of the whole situations. Remember, one thing we have assumed here, the gamma we have assumed in this equation is isotropic, which is not the case. So there will be some deviations when the gamma is anisotropic. That is what I said. The grain boundary nature dictates whether the grain will shrunk or grow. So depending on the type of things, type of the nature of the grain boundaries, because this gamma is, I am not going to discuss with you, gamma depends on many things. Depends on the crystal orientation, depends on the double derivatives of the gamma with respect to crystal orientations. So by that we can actually make the sign positive. There are situations. Let us not get into those complex situations. This happens when you have special grain boundaries. But normally, normal grain boundaries, so whatever I said will valid. Okay, let us stop here, and basically I am going to start a new topics in the next lecture, but I will discuss at the beginning of the lecture the kinetics of the grain growth a little bit. first 5 to 6 minutes, 5 to 7 minutes, and then we will start the next lecture.